you for reaching out, and it has been a really wonderful workshop. At least to me, I know that many of you have suffered quite a lot. So yeah, this title I visualized it like 3 weeks ago when Rogerio contacted people to start submitting their work, and so let me tell you in advance, I will not scrutinize anything, because when I was building the talk, I realized, well, it's not an easy thing to scrutinize inflation, and perhaps I'll touch upon some points in that regard. But what I will do in the end is to sort of give you an overview of cosmic inflation, and then I'll touch upon some subjects that I thought, well, it will be interesting for this kind of audience that is attending this workshop. Okay, so a very quick overview of why do we think that there is a period of cosmic inflation. And so you're all experts on cosmological perturbations, and so what we know is that the cosmological perturbations we observe, if we evolve them into the past, they are all superhorizon at some point. And we need to fix initial conditions for them. Yeah? And what we know about these initial conditions are basically 3 properties. And these properties are adiabaticity, Gaussianity, and scaling independence of the power spectrum, or the spectrum in general. So the thing to emphasize here is that these conditions were actually known from before the invention of inflation, right? So these are things that people in the 70s already realized about just doing statistics with very low quality data at the time, but this was well understood that these were good features for the initial conditions of contrast. Yeah.
They knew that it was Gaussian. Is this due to the central limit theorem?
That was the argument, because the realization was that these perturbations were evolving linearly at the very early universe, so when the universe was dominated by radiation. And so they sort of the idea there was that, okay, let's assume that the mechanism that gave rise to these perturbations, whatever it is, we don't know, had also this feature inbuilt, that the mechanism itself created these perturbations in a linear manner. Yeah, it was an assumption, but was well informed, because at that time they realized that in a very hot environment, the dominant perturbations were going to evolve linearly. Yeah, that was the idea. So it was a guess, but was a well-informed guess. So it was a wild guess, in fact, because you're saying, okay, the mechanism, which I don't know, has this feature also inbuilt, that they're going to be behaving. So what is linear or not depends on your definition of the actual variables, right? So if the mechanism was really evolving something which was not these perturbations, was something different, perhaps there was a nonlinear relation between that variable and the actual perturbations. Yeah. So this was a guess, but it was related to the central limit theorem, of course. But this is a feature of the mechanism itself. So there is a difference. Yeah. Yeah. So adiabaticity. Well, let me go through the 3 features, right? So what does adiabaticity mean? Basically, that any contrast during the early universe, as far as we know, at least radiation, neutrinos, baryonic matter, and dark matter, they are all proportional to a single fluctuation. Yeah, the idea is very simple. It's just that if the temperature rises locally at some point, every density will also rise together. So they're very well efficient thermalized, right? So that's the idea. Any deviation from this will usually decays very fast. Yeah. So this was well understood at that time. Yeah. And so we can actually choose what's going to be the variable that we decide is going to be the variable leading this proportionality, and we can choose it to be this the curvature perturbation. So this is just one choice. It could be any other choice, but this is a very comfortable choice, is to work with the so-called comoving perturbation the curvature perturbation. That's a mistake. the curator perturbation in co-moving gauge. It's just a choice. So has not always been the favorite choice. The next feature is Gaussianity. This means that now that we have a perturbation to work with, the co-moving perturbation, we can we need to decide the statistics, and this is sort of going back to the previous question. So the guess is that these are distributed according to a Gaussian distribution. Yeah, it basically means this. So there you have the covariance matrix, which is basically just telling you something about the amplitude of these perturbations initially. And so, whoops, I don't know what happened. And so this introduces the power spectrum, which is there in that P, that function P. And then the next decision that we need to make is what is the shape of this power spectrum, right? So we went through already two features. So the next feature, which is a decision about the power spectrum. And the power spectrum can be written in this way. We just factorize it with a volume factor, which is 1/k3, times something which is dimensionless. And given that this is a dimensionless function, the obvious choice is just to choose a constant. And if it is not a constant, then the next two obvious choice is a power law, right? So that's a guess again. This was made during the 70s. And well, if you go to data, of course, we know that the spectral index of this power law is sorry, yes, this is correct. The NS is equal to 0.96, more or less. And so it's almost a constant. So all these three assumptions were very well-informed assumptions, and they work actually. So that's pretty amazing. Yeah. So one can do a lot of cosmology without knowing about the mechanism that gave origin to the initial fluctuations. That's pretty awesome. Okay, so let me, well, I will be reviewing all these three features. Let me just immediately, before attacking inflation, let me tell you something about Gaussianity or non-Gaussianity, because it will be a subject during the talk. So we can, of course, we can wonder whether this is a correct guess, yeah? And we can so explore deviations to Gaussianity, yeah? So this means altering the statistical distribution of the curator perturbation. And for example, we could have deviations like so, okay, the one that you see in the picture, yeah. So how can we choose this? How can we do this? Well, first of all, we can test it, right? So we can test whether there are or not Gaussianity. So, and the CMB will be the cleanest way to do it nowadays. Okay, you can test the statistic by performing 2-point statistics, 3-point statistics, 4-point statistics, whatever. So you can test this. Okay, so by testing the Gaussianity, you're really testing deviations to this ansatz that you see in the screen, and the next sort of the lowest test you can do is to the bispectrum, and we just saw a nice talk about how to constrain the bispectrum, a very particular type of bispectrum, the one which is called the local bispectrum, the local shape. Yeah. So that's the definition of the bispectrum. The bispectrum is just the function that multiplies the delta function, and this is the delta function has to be there because we are dealing with spatial translation invariance environments, and so now we need to guess what's the simplest deviation to Gaussianity that we can do. Remember, we're in the year 70s. Yeah, we don't have inflation yet. So at that time, the guess was this. It was called local the local ansatz. Yeah. So local ansatz consists of saying, well, whatever mechanism operating in the early universe that produced the perturbations, well, it was not really Gaussian. So the Gaussian variable was some variable that's part of the mechanism. We don't know the mechanism yet. And the stuff that we observe is not really Gaussian, is related to a Gaussian variable, but in a nonlinear way. So this will be the guess. Yeah.
Was this really proposed in the 70s, or you're just saying that it could have been proposed in the 70s?
No, it was really proposed. Yeah. Don't ask me when exactly, but it was these things were all discussed early on. Yeah. So people like Seldovich, Peebles, they all thought about this.
Rogero was there, you know. Thank you.
I mean, Princeton during the 70s was the place to be regarding all these discussions. And yeah, so this is called the local onset before inflation. I repeat the idea, and it's just a simple relation. It's a nonlinear relation between the Gaussian variable and the actual observable. Yeah. Of course, you can continue this. I mean, it could be an arbitrary function relating so the thinking here is that, okay, we know that statistics is nearly Gaussian. Yeah. So let's try a small deviation. Let's not go crazy with this. Yeah. And if you try this, then you can compute the bispectrum. Yeah. And the result is that one. Yeah. This is not a prediction from inflation. It's just it's a guess. Yeah. And so this is what Walter precisely displayed in his talk, and there you have the parameter FNL local, yeah, and that's how it appears in the bispectrum, and there you have the power spectrum appearance in combinations, yeah. Now that you know this, you can move forward and you can say, well, let's try other things, yeah. We learned quite a lot by doing this guess. Let's try other shapes of bispectrum because we know that there is a sort of structure that we learned from this guess. So then you say, okay, let's. This is more modern. I have no idea whether this was tried in the 70s, but let's just try this type of parameterizations when we have some parameters, some amplitudes. The power spectrum, this A squared is basically just the amplitude of the power spectrum, yeah. So you just take it at some given value, some pivot value for the scale, and then some shape. So this is called the shape, yeah. Which is kind of it's just a generalization of the previous relation, yeah. And then there are different shapes in the literature, and people choose shapes in such a way that they are kind of easy to distinguish among them, yeah. So inflation might predict, well, it predicts infinite shapes, but then it's a good strategy to focus on those shapes which are quite distinctive from one another. Otherwise, it will be very difficult to extract them from the data.
Is one of the momenta.
So this is just a plot of the shape, fixing two momenta and allowing one of the momenta to run. And given that there is this restriction of that all the momenta have to add up to 0, then this is a good way to visualize. You project out a lot of stuff that you're not interested in. Mm-hmm. And yeah.
So they should also depend on the angle between the momenta, no?
Well, it happens that because of the direct delta restriction, you can manage a lot of you can do a lot of algebra to eliminate the angles and make it a function which depends only on the momenta. That's for simple shapes, because then you have other shapes. You might have heard about the cosmological collider program, where indeed then you start having more stuff into the shapes, like more angles, and then you could have spin dependencies on the particles. So these are really predictions from, if you want to connect it to inflation, it will be shapes that appears, for example, from scalar induced perturbations.
The angles are fixed by the type of the triangles. Yes.
Yeah.
Like the quattro, we have like equilibriums and.
Yeah. So there's a lot of things going on here, but what I want to emphasize that these are things that you could have thought about it without inflation whatsoever. These are just trying to think of shapes which are orthogonal to each other. So all of these are shapes which are mildly orthogonal to one another by if you define certain products in K-space. Yeah. So they help for projecting out the data, and that's it's a clever thing to do. Okay, so these are some forecasts for coming surveys. This is from a paper 2 years ago. So I'm not really updated about this, and I think most of you are way more updated than me about this. So you can see that with FNL, well, Walter already let's talk about this. So I'll just continue. Yeah, but there you have. These are projections on future experiments. Okay, so back to prime model perturbations. Now we need to understand how did this initial fluctuation, super horizon fluctuation appear, right? And that's how cosmic inflation enters. Cosmic inflation is basically a change of rules. You know, so let's say, okay, we need something that gives rise to this initial condition. So let's build something. Let's build a mechanism in such a way that this fluctuation that we see there, which is the initial condition for cosmology, is the end product of a mechanism. Yeah. So let's change the rule, and the simplest thing you can do. I mean, this is after the fact, of course. It wasn't that simple. Is to just let's decide that the space-time evolved very differently before this initial condition. Yeah. So let's decide that the Hubble radius was frozen at some point before this initial condition, and that well, that's it. That's basically, and that's what we call inflation. So inflation is just a change of rules of how the Hubble radius behave. Yeah. So the Hubble radius is basically constant, and because of that, then wavelengths, which were plotted here, wavelengths stretch exponentially in time. Yeah. And therefore, you change completely the relation. Now, any superhorizon fluctuation must have been subhorizon in the past, and now the question about initial conditions changes a lot. Now the initial conditions are basically have to be put somewhere into the past. Yeah, but it's actually simpler. It's now the initial conditions are really put in a surface in terms of wavelength, which goes parallel to time if you want, because you're just saying, well, there's a minimal wavelength where the environment is just the vacuum. So you just impose that the environment is the vacuum, and that gives you initial conditions. So it's a very clever way to not care about the initial condition. You just say, well, at superhorizon scales, you don't realize that the universe is expanding. You have no way to know that, and the space just looks like Minkowski and is devoid of anything. Yeah. And that's the way that people fix initial conditions for inflation. It's just a statement. So it's a very economical way of understanding these initial conditions in terms of trivial initial conditions. Yeah.
The vacuum is well defined because it can have going to day.
Yes. I mean, there's subtleties, but I would say in very broad terms, it's well defined, and there's some issues that I don't think they're issues at all, as the Transplanckian problem that some people bring in. But I think the argument is that you at very short wavelengths, you don't see the universe expanding. There's no way. It's like we're in this room. We don't see that we're not getting bigger and bigger. That's also going on in inflation. Yeah. So that's the argument. And that's good enough to get. Well, those initial conditions have a name. It's the Bunch-Davies initial conditions, but basically it's that.
Of this, but these initial conditions, it was homogeneous.
No. It's the statement is that if these are wavelengths, right? So okay, I'm plotting wavelengths also in a coordinate space plot together. So that's not very good. But if you think in terms of wavelengths, then at very short wavelengths, when these wavelengths are very small, we're really the physics that is in charge of those phenomena is not aware that you're in an expanding universe. Yeah. Why? Because the Hubble radius is just too large for very small wavelengths. Yeah. So you're back to just Minkowski. That's it. There's nothing else to do. And the Bunch-Davies initial conditions is basically that statement that at very small wavelengths, you have to recover Minkowski, and there is nothing weird. It doesn't matter that your space-time is super curved. Nothing can go wrong at very short wavelengths, unless you start hitting, let's say, the Planck scale. But the idea here is that we don't want to get to the Planck scale. Yeah. So the Hubble radius will be way larger than the Planck scale. Yeah.
But talking about the modes.
Oh, I'm talking about the modes.
But The dynamics of the field does depend on the background. No?
Of course, yes, yes, yes. This is just how to impose initial conditions for the modes that are part of the field, and the field could have nonlinear interactions, and then we start getting into the interesting part, of course. Yeah, yeah, yeah. I'll get to that point. Okay, so now we're still dealing with the comoving curvature perturbation. So now it says so you see that the commutative curvature perturbation continues to be the same actor here. It doesn't matter. We just need space-time to exist. Yeah. So you just continue working with it, and now you have to write a theory for it. And now it's not just an initial condition here. It's just something dynamical that you can study. And of course, what I say is that the space-time looks like de Sitter in this time. And we just do quantum field theory in curved space, and we need to write a theory for R at this time, and we can do it. Yeah, you just pick up that metric, that inhomogeneous metric. You just plug it into your favorite action with some type of matter field. Of course, this is a scalar perturbation, right? And in gravity, there's no scalar perturbation, so you need some scalar source for it, some dynamical scalar source. But after you consider that, you generally, I mean, not generally, always will get some action for R, which will look like this, yeah, with some modification that could happen in different models. But roughly speaking, this is the generic type of action that you get for R, yeah. Okay, so that's the game is to figure out what's the dynamic for R, for the Curie perturbation at this time during inflation, yeah. And then the idea is to predict the statistics at this surface, yeah, at the final surface of inflation, the initial surface for cosmology. Yeah? Okay, so how do we do that? We want to compute endpoint correlation functions. That will be the outcome of this game, yeah. So if you do quantum mechanics, I think implicitly I say that during that time the universe is empty, so it's very simple. There's nothing going on except for quantum fluctuations, yeah. The universe expands fast enough to dilute any particle content. So in the end, even if you started with some thermal bath, let's say you had a big bang at the beginning, you have inflation, and that will dilute the universe. And so you really want to compute just expectation values using quantum field theory. There's nothing else to do. And in quantum field theory and quantum mechanics, what you usually do is just to write your variable in terms of some propagator operator. That's what you mean there. And then there is some what's called the interaction picture field. Yeah, these are technicalities, but the thing is that there is a well-posed procedure to do this. If you knew the action from which I wrote before, then you know the Hamiltonian, and so you can do this systematically. Yeah, and then you can compute endpoint functions. And there are three methods to proceed, and which are widely used in literature. One is the Hamiltonian in formalism, which is less used today. Yeah, but for historic reasons, almost every important computation was done with this method. So the Hamiltonian method is just to compute this with this expression by expanding this operator there. So you expand it, and then you have quite an ugly product there. With a lot of commutation relations that you need to perform this, you expand the operators in terms of creation and annihilation operators, and now it becomes a mess. Yeah, you need to perform these contractions, but it's very systematic. I mean, it's difficult to make mistakes. It's just no, it's actually quite easy to make mistakes. There were a lot of historic mistakes actually during the 90s, especially when people were trying to compute three-point function, for example. That was a real challenge. Yeah. And the three-point function is the simplest thing you can compute here, yeah, beyond the power spectrum, which was the first thing was computed. Okay, so that's it. I won't say anything else about the Hamiltonian method. Then there is another method which is widely used today, which is the path integral in, I mean, both the Hamiltonian and the path integral are both part of what is called the Schwinger-Keldysh formalism. There are different versions of it. Yes.
Maybe you said this and I missed it, but I guess like in normal QFT, you're normally calculating something that's like an in and out in terms of the external states that are going in. Why are we doing in here?
Yeah, precisely because the final product that we want are correlation functions. Mm-hmm. Yeah. So as opposed to amplitudes, where you have particles that are in the in states that will scatter and then will go out. So the in basically is just telling you that. Well, I think let me answer you with diagrams that we'll show later. I think the rhetoric answer will be simpler.
Isn't just, sorry, just on this, isn't just a simple issue that you want initial conditions and you want to let them evolve. In particle scattering, you want fixed initial and
Fixed out.
particles.
Well, let me
Boundary condition.
Yeah, you're just saying that you're looking at the probability to have that final output as opposed to what is the initial state and then evolve it using some deterministic.
in a sense, the answer is already here in this expression, because you see that you have the unitary operator appearing both at both ends. It's everywhere, right? The unitary evolution operator. But then one version of it is evolving to the past, and the other is evolving to the future. Yeah, as opposed to in the case of amplitudes, where you are evolving everything to the future. Let's say so it's a technical answer in a sense. But with the process, we'll give an answer. Yeah.
Are you considering just linear perturbations, or are you going to have?
No, this is the full thing actually. So this here will have every possible interaction.
Okay,
So
makes sense.
this is a mess. It's really people have only done a few low order computations in this using this scheme. It's
So we are considering higher contributions in the action that you showed.
you can consider all of it. Yeah, that's the idea actually. Is to learn how to go as far as one can.
But there is no way to resum.
No, I think there's been a lot of progress with summing things, and not everything, of course. Not everything. It's a challenging problem, of course. Yeah. So the path integral in is let's start from the same expression that we had before this, but let's not expand U. With path integrals, you can rewrite U in a different way, in a path integral way, let's say. Yeah. So that's it. So you just rework U, and you write in terms of the Lagrangian, yeah, or the action, and you end up with this relation. So in a sense, this is also part of the answer to about the in is because here you see again like two sectors. One is going into the past, the other into the future. So you see two copies of this of the action. Yeah, that is evolving the system. Yeah, one is going backwards, the other one is going into the future, and you have to sue these two different evolutions at the boundary, at the final time where you want to compute endpoint correlation functions. So you impose that the two copies have to coincide at the end. Yeah, they have initial conditions into the past, but at the end they have to be the same field. Yeah, so that's a boundary condition on this path integral.
There's a typo there.
Yeah, there must be a typo.
Because the exponential, one is R plus.
Yes. One is saying, I don't know which one is R minus. One of them is R minus. Yes, you're right. And I guess it must be this one. And so you have two copies, and then well, this gives you a mechanism to compute correlation functions using path integral ways methods, that means diagrams, right? So you can define some now that you know this, you can define some partition function, and from the partition, once you have a partition function, you have diagrams basically. You have all the diagrammatic rules. And now let me show you schematically how it works. You want to compute an endpoint function. You will have some interaction that's defined by your theory. So you have the action, so you know what's that interaction. But now, unfortunately, since you have two copies of these fields, then you have double the number of interactions really. Yeah. So this is an example where you have one copy, which is the plus copy, and the minus copy of the interaction. Yeah. So that's sort of a headache because there's a lot of structure going on. And you only realize at the end of the computations that there's a lot of cancellations because of this. It's like this is a Feynman diagram. So when you perform computations in QED, you realize at the very end that there's a lot of miraculous cancellations. Here is similar, yeah. And so there's a lot of efforts now trying to understand the structure, which might be just just part of the method in the end. There's nothing really physical going on.
If this is a Feynman diagram, it's an n loop Feynman diagram.
Then you can add loops if you want.
So this is loops.
Oh, sorry. Let me clarify a little bit these things. This line on the top is sort of the final surface, is the time surface where you want to compute the endpoint correlation functions. So these are external legs.
Oh, so there are 3 levels.
This is a tree-level diagram. Yes.
But
Yeah.
endpoint, I mean,
And
It's an endpoint. Yeah.
Feynman diagram, they're not only more difficult if you go to higher loops, also if you go to higher external legs, it becomes more difficult.
Exactly. Yeah. And then you can have with more vertices, and that means, of course, more diagrams because you need copies, black and white copies, like plus and minus degrees of freedoms, and so the proliferation of diagrams becomes pretty impressive. Yeah, if you just with a few interactions already, it becomes quite hard. So going back to the question about the in, it's like here you only have final states. You have nothing feeding. There's no particles colliding here. Yeah.
So what is the block in the tree-level diagram?
Yeah.
Maybe the under block, the white one.
It's some vertex of that the theory gives you. I don't know which vertex. Is you need to write first a theory for R. And this will be some, for example, this is an endpoint diagram, so it's a vertex with n legs, yeah. So we will something to the power of n of the R field, yeah, in your action.
And when you say R field, you're not saying it this which is current.
No. Well, it will be related actually. The curvature perturbation will be literally a perturbation to the curvature of the Friedman-Robertson-Walker metric, yeah. Well, the gradient of the curvature perturbation, as a matter of fact. Yeah?
do you have any gauge dependence?
So this will be in a given gauge already. So this is a gauge independent variable, but you first have to go to that gauge to work with that.
So diagram by diagram, there's gauge.
Sorry?
Diagram by diagram, there's gauge, but it drops out in the end.
Oh yeah, that's true. That's so.
In the gauge to do the calculation.
Well, but I presume what you can do is you can work in a gauge agnostic way. So I have some parameter tracking your gauge dependence and what will fall out. Yeah.
Exactly. So that happens.
Sorry, what's the comma 1 and comma 2? I didn't.
Oh, the one is just to say that these are diagrams which are first order in whatever vertex you have, and this will be second order in the vertices. Yeah. Of whatever vertex. The way that I haven't, these are very, there is little information here. I'm not telling you how to organize the theory perturbatively. That's up to you. That's up to your theory. And without knowing the theory, this might be meaningless whatsoever. This is just a scheme to write that diagrams.
It's little more than a heuristic.
Yes. You need a theory to make this concrete. Yeah. So the purpose of this picture was just to show the techniques that are used to compute the correlation functions. And you can add loops, of course. And then this is something that I've been keeping me busy lately. And we have a couple of papers recently addressing the computation of loops, which I have to say lately in the community, there's been the realization that we do not agree with each other how to compute loops. And there's been a few papers that have made the field burned, and then there's people disagreeing that whether a given computation in loops was correct or not. And I think it makes us visualize that we haven't agreed on very basic things regarding perturbative computations in, for example, in very simple setups like just pure de Sitter or whatever. So there's a lot of things going on right now there with a lot of disagreement, which is quite interesting. The wave function of the universe is the third method that is widely used nowadays. So let me start from this expression, which I already shown. This was our previous method, and let's rewrite it. So notice that it kind of smells. This looks like you're really computing a single path integral in which you could identify a single PDF, yeah, single probability distribution function from where you define the partition function, right? So there must be a way to rewrite this, and this is known from before inflation. Actually, this is what's called the wave function. This is just quantum mechanics in a sense. It's simply the statement that the PDF is just the square of the wave function, yeah, which is true in quantum mechanics, and this is quantum mechanics after all, so it's true here. And it just happens that the wave function is this object, is exactly as it goes in quantum mechanics. Yeah. You have to be careful about the boundary conditions, right? So you need to impose that initially what I said before, the fields look Banch-Davis, there is nothing going on at very small scales, and that the field becomes your whatever field you need at the end, right? So it's this suing that I mentioned before. Yeah. So this was very early on studied by Hartley and Hawking, precisely to understand inflation better. But it was really developed without too much notice, actually, by Maldacena in his famous paper on the bispectrum. And then very recently, people understood much better what Maldacena was saying in the paper, and now it's widely used. I recommend this recent paper if you want to get into it. These are simple. This is well, it's not really simple, but it's an alternative method, right? So you can now just write the endpoint correlation functions using that new object. This entails Feynman rules again, but these Feynman rules are different. Now the object that you're dealing with is the wave function of the universe. That's the quantity that you would like to know, that you will later use to compute endpoint functions. So first you need to know what's the wave function of the universe. That's the first stage. So this is a two-stage problem. Yeah. So in the first stage, you need to understand what is the value of these coefficients here. These are called the wave function of the universe coefficients. Yeah. So that's an example. Just as you have multiple coefficients. This is just psi3, and to compute psi3, you need Feynman rules. Yeah. And so the wave function of the universe has Feynman rules which allow you to compute, for example, psi3, psi4, and you need to know the vertices. The good news is that you don't have the double counting of vertices. You have only one vertex per interaction. That's good. The bad news is that now you need two stages. So you still have to work a similar amount compared to the previous method. So you can compute loops, of course. We also have a recent paper on the wave function of the universe regarding loops. This came out.
Well, with the wave function of the universe, you're thinking about Sitter space always, or
no. You can implement it on whatever homogeneous background and possibly non-homogeneous background too.
then you can end up in like a time problem of the validity equation, stuff like that. So you're
I guess
into this. That's why.
Yeah, I guess so. I'm really more familiar with the Sitter setup, to be honest. But people use it for quasi de Sitter and I don't know how beyond you could extend it.
Here you're thinking about the Sitter space.
Yes, and quasi de Sitter. I mean, yeah. And then you have a second stage where if you want to compute endpoint functions, now you need new Feynman rules. So there are two sets of Feynman rules: one to computing the coefficients, and the second Feynman rules are to compute the endpoint functions out of the coefficients. So now the coefficients are vertices to compute endpoint functions. Yeah. So this is a two-stage problem, and of course you can also compute loops, and that's a mess because now loops are sort of mixed. You have loops coming from the previous stage that have to combine with the loops of the second stage. Yeah, and they have to give you the same loops of the Stringer-Keldysh formalism before. So everything has to fit, and they fit. And we have a recent paper on that where we show that the two stages in the end give you the same loops at the final stage, even if you have an infinite set of loops. So that's
Sorry, at this stage before you go on your calculation, for example, the one plotted there, it will give you information of what's in it.
Right. Well, so what's the purpose of this? Is the main purpose is to compute endpoint functions. These guys over here. And these endpoint functions basically encodes all the statistics of the initial fluctuations for cosmology. My first picture, remember, that we need to understand the initial data for the rest of. So if everything is Gaussian, all of this is a waste of time, because here we're computing, let's say these are connected diagrams, which means that are non-Gaussian diagrams. These are all like the connected diagrams basically tells you something about the non-linearities of the system, right? Just as in particle physics, it's the same idea. So we want to compute these endpoint functions to understand the statistics, which presumably is non-Gaussian for the rest of the universe.
So moment, would it be possible to have some confirmation, some data?
Well, you have to ask Walter and the rest of the crowd here. Yeah. Okay, so I feel that I'm awful with time right now.
No, it's
Okay.
okay.
Okay, so let me go through now finally I can, after giving you all the tools, okay, let's be concrete about inflation. So vanilla inflation, and probably this will be it. I mean, there might be nothing else but vanilla inflation. So this was an extension to the original idea by Starominsky and Guth, which is that picture over there, right? So it's you have a period of inflation where you have basically a potential energy which is almost constant, and then you exit it by approaching to the minimum of the potential. So if this happens slowly, so this slow roll inflation, then you have the slow roll parameters, which will be small as long as you are slowly rolling. Yeah, that's the idea. And they have information about the shapes of the potential. Yeah. The main thing is that well, you in this picture, whatever the scalar fluctuations of the field that you're putting in your model will become the source of the curvature perturbation that we want to compute endpoint functions. Yeah, so you can write an action for it. Yeah, and that's the form of the action. Schematic form. I mean, there are many more terms. It's a way more complicated object, but this is the main idea. Yeah. And now that you have this action, you can compute correlation functions. So let's start with the linear part. So the quadratic part of the theory, which gives you linear perturbations. You use the Feynman rules, and you get this. It's a triple computation. There's no nonlinearities here. And this is what you find in the end, right? So this is a famous prediction by in the 80s, not only by Mukhanov and Chibisov. I don't know if you are aware, but there was this famous workshop at Cambridge during the 82s, precisely. And there was a lot of competing teams trying to compute this power spectrum. And in the end, Mukhanov and Chibisov were kind of won the fight, but in a sense by luck, because they were working on a specific gauge, which in the end everybody was confused whether this was the right gauge or not. And in the end, that was realized that yes, all the computations are equivalent. And in the end, this is what I want to say is this is the result. Yeah. So you have the amplitude of the power spectrum and the spectral index, and those are the values that connect the prediction with the model. Yeah. So there you have epsilon eta. What about the cubic part of the theory that gives you the bispectrum at tree level? So this is just the simplest computation. So we perform this computation in whatever method you want. This was done by, I mean, it was tried by many people, but now we know that Maldacena was the first one to do it correctly. And he used the Hamiltonian formalism to compute this. And this is the result, basically. Yeah. And you see the parameters. You see that it's suppressed by slow roll parameters. Yeah. So it's a small signal coming from inflation. Yeah. So this predicts, let me summarize, predicts, remember that I introduced the types, the shapes. So this predicts that the shapes of non-Gaussianity are very suppressed, or of order epsilon and eta. But there is something else, and this was realized more recently, that FNL, local FNL, that Walter spoke about, actually the prediction is exactly zero. Yeah. Why is this? Is because you're actually you might know that the Maldacena predicted that local FNL is proportional to the spectral index. Yeah. But if you're careful about how you measure this, you have to realize that that our local cosmology is flowing a free-falling observer, and if you correct by that, you realize that there are gauge. So you have to compute the observation in the correct gauge independent variables, and you discover that there is a cancellation of Maldasena's prediction. Yeah. So the real Maldacena prediction is that FNL local is equal to 0. That's the outcome. This was first realized by Tanaka Urakawa, and then these other people also corroborated this with other ideas. Yeah, but they all agree on this. Yeah. This has been quite difficult to swallow, actually. Not everybody agrees, by the way. But so I just mentioned it. It's an interesting thing, but it's quite important because
Not everybody agrees now, or
not everybody agrees now.
even now.
Now, yeah, yeah, and okay, tensor modes, same story, blah blah blah, and you get a prediction for the power spectrum.
But Gonzalo, even if we single field polarization, if you agree it's 0,
Yeah,
other models will be non-zero.
other models will be non-zero, and that's why it's so important.
Practice doesn't change too much because it's going to be very small or not very small, right? And it's
No, but I think it's important because
you see some other one and you see it's not single field proliferation, or it's going to be very hard to.
no, I think it's very important because Maldasena's prediction originally was it was called the consistency relation precisely because it fixes two observables into a single relation. When you have that, is okay. It's a very important thing. But this amounts to say no. There is no such a relation between two observables. It's just there is nothing there. Yeah. So it was a target to get to, right? So let's push observation to FNL of the order of something that we already know, which is the spectral index. So it was something to look forward for. Yeah. Now we don't have anything, in a sense. Yeah. So you see, I think it's important. So it would be important if we all agree that this is a real thing. Yeah. Yeah. So this is a summary that you've seen many times. And the one thing I want to stress here in this picture is that current observations are putting a lot of tensions on model builders because we're discarding convex potentials. And now if you insist on single field inflation, they have to be concave. So the shape of the potential has to be going down as you and that's it's interesting, right? So if you keep pushing this bound to lower values, then the potential has to be even more and more concave. So there will be a hierarchy between eta and epsilon. The other thing I want to stress is that there is another consistent relation, which was from before Maldacena, which is a relation between R and NT, that's the spectral index of. I think this is really important. Is if CMB observatories detect tensor modes, I will not be convinced that that's the final proof that it was inflation. That's my personal opinion. But if you confirm this relation, then I think that's it. So we can really claim, okay, there was inflation going on because this is a prediction. This is a true prediction of inflation.
That's for single fields.
This is for single field. I'm just assuming, but you can always modify things as will. But if you get to measure this, then okay, end of the story. It's a single field and there's nothing else. Yeah. Okay, so mini summary of the first part, and then I'll try to go very fast. So yeah.
So if you keep pushing R down, then it means that eta must be important.
So if you increase the boundaries on R, epsilon will become smaller and smaller.
So
because
eta,
R is basically epsilon.
yeah. So eta must take into account the.
Eta acquires a negative value, but it approaches to 0.035. I don't remember 0. So it's something small, but it approaches to a value which is fixed by the spectral index. Yeah.
So eta will be more important than epsilon as R goes down.
I mean, both are important, but
No, numerically, I mean, it will be
yeah,
higher.
yeah. It's just that you will learn that epsilon and eta are very different quantities in the model itself. So that I think so. If you observe R, that would be a dream come true. But if you don't, you still learn something about the model building side. So I think that's still optimistic. So this is what the second point is what I already mentioned. But this is really a personal opinion, and if you measure FNL local, then this is not a prediction from single field inflation, so you will rule out at least a good bunch of models. Okay, let's.
So if you measure, sorry, as I know you're but if you measure R equal -8 NT,
Yeah.
and you measure FNL, then you're going to confirm and discard single field equation.
But that will be.
How would you feel?
That would be fantastic. Come on. It's, marvelous. I mean, please. Because it will mean that we don't understand anything. Okay, so fast forward in time. This is kind of historic. At some point, Garriga-Muganov wrote this theory, which is P of x or P of x phi, which is just a single field, but in a generalized form. And from effective field theory arguments, you will say yes, the most general single field model has to have this form. Yeah. And the nice thing about this is that this combination here introduces a new quantity, which is a measurable thing, which is called the speed of sound. Yeah. And it really is the speed of sound of the fluctuation. So if you see how the action looks like, it will look like this. So this quantity appears in that way in the quadratic part of the theory, but also appears in the cubic part. Yeah. So you turn on the speed of sound, and it pops up in more than one place in your theory. So this was well understood later by these papers. The second paper is the famous paper of the EFT of inflation, which gives a more general rationale of why this is going on. So they realized that this is a very general rule that's not only true for single field inflation. It's just even a multi-field inflation should have this in some limit. Yeah. And so how does this modify our picture of observations, for example? So typically, equilateral or other shapes of FNL will be enhanced by this speed of sound. Yeah. So it will go something like this. Yeah. That's good news because we can realize in very general terms that FNL in general could be large. Yeah. Just based on effective theory arguments. There is no reason why to rule out a large FNL in a sense. However, this was shown by Paolo and Matthias in a quite a famous paper by now that in the end the prediction for the consistency ratio doesn't change. It continues to be the same one as Maldacena's, and therefore, if we put this together with these works by Urekawa and Tanaka and the other authors, that means that even in a very general setup, effective field theory continues to be zero. Yeah. So that means that if you want to have a non-zero local FNL, you need something else. You need something active there. Yeah, it's not enough. It cannot be predicted by a single degree of freedom. In other words, yeah.
Are there any bounds from like physical consistency with positivity or something like that on what the sound speed can actually be before the theory becomes it?
Yeah. So you have always to be careful because since a small speed of sound enhances the interactions. Mm-hmm. So of course you might get into a non-perturbable degree. So that's why yes, you have to put bounds. However, it's tricky because these couplings also depend on scale. So in the original effective theory paper, they put the speed of sound just the way that I showed. But actually, when you reduce theories, for example, some multi-field theory back to single field, you discover that it's not just straightforward. You also have some k-dependence, mm-hmm. And the k-dependence usually affect the let's say the unitarity bound that you thought it was active in the original effective theory. Mm-hmm. So it's a bit more complicated, but yes, that's what is you have to be careful. Yeah. Good. So given that local FNL seems to be such a robust zero local FNL seems to be such a robust thing, let's explore a wider set of theories. Yeah, I work quite a lot on this subject, multi-field inflation, and to visualize it, consider this picture where you have a two-field landscape, and some potential, whatever, and then your trajectory will try to go through the trough of this potential, and that defines in the target space some trajectory. And now you have a new phenomena because whenever the the target trajectory in target space, the trajectory experience a bend, yeah. So it could be a straight line, yeah. But you could also have bends in general. We can rule it out. Then this bend, this is let's say this is the angular velocity, if you want, this alpha parameter here, will turn on couplings between R and some other field, some isocurvature field, yeah. The isocurvature field, so the curvature perturbation will be basically, if you want to geometrically think about what is the curvature perturbation, how it is connected to this pair of fields, the curvature perturbation will be fluctuations along the trajectory. Yeah, so these are tangential fluctuations to the trajectory, and the isocurvature fluctuation will be fluctuations orthogonal to the trajectory. Yeah, normal to the trajectory. Yeah. And what I'm saying here is that whenever there is a bend in the trajectory, that will wake up couplings between these two pair of fields. Yeah. So that, of course, you could also have some potential, some self-interactions for the isocurvature field. Yeah. So the bottom line here, the curvature perturbation continues to be the same curvature perturbation as before, but now the action is enriched because it has the possibility to interact with another field. Yeah. Okay. Okay. So now you have new interactions. That's it. And people have studied the effect of this interaction. This is the quasi-single field prediction for the bispectrum. And you discovered that there's a new shapes. Yeah.
To incorporate those relations in single field, one assumes a vacuum state.
One assumes
A vacuum state.
yes, yes.
In this case, since there will be interactions between curvature perturbations and isocurvature ones, what guarantees that you can assume an initial vacuum state?
Right. No, the argument will be the same. I mean, you assume that at very short scales, there's nothing really going on. Your state is approximately the vacuum, corrected by interactions, of course. This is always the interacting vacuum. But that's assumption. It's an assumption. So you can modify it.
But so it's not Bund-Davis, since it's
It could, no, it is Bunch-Davis. It is it's an assumption. Yeah.
Oh.
But it's you have to assume something always.
Okay, so the idea is you assume that for small scales, the interactions are not relevant, so I can set Bund-Davis.
Yeah, that's assumption. Yeah, so you can always write a theory which violates that assumption, but we're doing the one does whatever one can do. And so this
What is quasi-single field?
because they saw that mild modifications to the bispectrum of and they sort of it's just a name, to be honest. The idea was that this field, if it has a mass which is of order of the Hubble scale, it won't be too massive, so that this is not single field, but it won't be either a massless field. So it was a quasi-single field. So the phenomenon was in between something which was single field, if the mass of the field was too heavy. Then later on, well, there was a succession of papers. I also wrote some papers, but I didn't put them here. People started to work out this diagram, and they discovered a very interesting phenomenon that the properties of whatever field you have here, in this case an isocurvature field, but it could be something with spin, for example, will transfer its property to the 3-point function, and that was called the cosmological collider signature. Yeah, and that has been a quite active. Okay, so in my last 6 minutes, or you say 5? 3. Okay. Just very quickly. No, I promise that I'm almost done. Just want to comment on two phenomenon that I work on. I thought they could be interesting for this audience. So one is about primordial black holes and gravitational waves, which has been a subject of intense discussion during this workshop. So let me give you a preamble in single field inflation. Early on during the 2000s, there was in an appendix in this paper, the authors, just for very formal reasons, they discussed this possibility that the potential became exactly flat. Yeah. and they named this ultra slow roll. Yeah. Later on, Wilkini wrote a paper on this. He realized this that was very interesting, and Wilkini got all the credit for this idea. But Wilkini does credit Samis and Woodard. It's just that they have it hidden in an appendix. And later on, for example, Juan Garcia Bellido and Ruiz Morales, they took this as the basis for as a mechanism to create primordial black holes. So what's going on is that as the field get trapped here in this plateau, let me go back. So remember, the plateau is basically something that is very flat. Then something happens. The epsilon drops down to 0 very fast, yeah, extremely fast. Doesn't stay constant, and eta stabilizes to -6. That's it. And it's very weird, and people didn't pay attention to this, and they just thought this was something, a curiosity, until they started using it for primordial black holes. And because if that combination happens, the power spectrum gets enhanced widely. Yeah. So, for example, you have the CMB region of the power spectrum that we measure. Then at lower scales, you will have a very large enhancement. Yeah, that's the idea. Some people have discussed whether this is efficient or not. So, for example, there's this famous paper by Burns, Coles, and Patil, where they discussed how intense could this growth be, and they said that generally this cannot be larger than a power law which is k to the 4. You still have an enhancement, but it's very limited. Yeah. So with multi-field inflation, you already know that you can have bends in the trajectory. The situation changes quite a lot. You have new couplings which could enhance the power spectrum. Yeah. So recently there were 3 papers on the same week. So we put out the paper, and the next days came out the next ones. And we all had the same idea at the same time. Honestly, we didn't know that we were working on the same subject, but we all reached the same conclusions, that there is an intrinsically multi-field mechanism to enhance the power spectrum, which is very efficient. Yeah. And the idea is that if you have a very acute change in the direction for a small period of time, you could, that's just a modeling of this. Let me just go fast. You can actually make a prediction. This is it's quite simple in the end. You can just work it out analytically, and that's what's so nice. And this is the result. You get a very large enhancement of the power spectrum with a lot of structure in it. This is a comparison between the numerics and the analytics. So there's a lot of control on this. Yeah. Those are parameters that depend on the shape of the parameters. So that's to produce primordial black holes. Yeah? You already know that this enhancement helped to produce black holes. But regarding gravitational waves, we discussed different methods to produce gravitational waves, and you already mentioned in this workshop the scalar-induced gravitational waves of the same fluctuations that created the primordial black holes. As they re-enter the horizon, that they also emit gravitational waves. What we did here is to compute the primordial component of this. So let me explain a little bit this plot. The green line will be the usual scalar-induced gravitational waves produced at the time of the primordial black hole production. Yeah.
By the second order process.
By the second order process during radiation. Yeah. But the thing is that whatever mechanism you had during inflation that produced such a large enhancement might also have produced gravitational waves during inflation. So that's what we studied. And what we found generally is the signal is actually larger than the secondary one. Yeah.
Think that the power spectrum of curvature perturbations have an increasing amplitude, right?
Yeah, very wide.
Does the tensor power spectrum for first order tensor perturbations also have an increase?
That's what we're saying here. Yes, yes. So it's exactly the red line. You have a numeric and analytic version of it, and that's the statement that this also has the tensor on small scales, not on the scales for. So that's something I want to comment, and I think I have 0 time, so perhaps just jump it. And I want to say that another thing that I work quite a lot is to produce types of non-Gaussianities which you see this plot, you see the Gaussian prediction, and you see a non-Gaussian prediction coming from multi-field. So you can see by eye that this could not be parameterized just by the bispectrum, right? You all agree with me, you need all the endpoint functions, yeah? So this is just me saying, well, since you are all in the business of understanding what goes on after the initial conditions, perhaps this is a type of non-Gaussianity that's worth looking for. Like this is perturbative prediction. That Paolo Creminelli has also worked on this in the non-perturbative side. But this is a type of non-Gaussianity that generally I don't think we are searching for actively. Yeah, and we had an attempt here with the CMB data. We found perfectly Gaussian distribution. So that's it. Okay, my conclusions. I know that everybody's tired, so these are my conclusions. Thank you very much.
I just want to make an advertisement.